given to us in this problem, we are told that the net moment around A is 0, or if we sum all the moments that act around point A, it does equal 0. When we go into equilibrium, this will be true, but this is a special case in this section. Right? And we know that the value of P is 30 pounds. So we're looking for what is this value of F such that this is true, that if we sum up all the moments around point A, it's equal to 0. In general, in this section, we won't necessarily be making free body diagrams. Those are, we're going to be using free body diagrams if we're in equilibrium in this course, and then like EMCH 212, that's expanded. I'm just going to call it a diagram because sometimes here it won't be a true free body diagram because I'm not going to be accounting for everything in it. So what I can do here in my diagram is I want to make a picture so that I'm going to be able to find the value of F such that that moment equation is true. So I can have my utility pole here. I have my point A. This is 45 degrees from the horizontal, which actually is also 45 from the vertical. The other person is pulling at a lower spot on the pole. We don't know what the magnitude is, but we do know that it follows this ratio triangle with 4 is the horizontal, 3 is the vertical. They're pulling 12 feet above A, and the other person is pulling 18 feet above A. And I have a coordinate system. So we're going to see when we get into rigid body equilibrium, this is actually not a complete free body diagram because there are more things happening at A that I'm not taking into account in this problem. But as a diagram, it's going to work much the same way where we can add all of our moments together. All right, so it doesn't look that different than what we've been seeing, except that, again, F and P are not concurrent. They're acting at different places on this utility pole that emanates from A. And what that's going to do is that has an effect over the net moment they're going to contribute around that point A. So the equation we're going to use is the net moment around A is going to be 0 in this case. So what we need to find is what are all of the things that contribute to the moment around A. In this case, when we have a force that is a distance away, some distance away from that point, we're going to be able to see what the moment's contribution is due to that force. So again, thinking back to kind of the wrench, we're applying a force a distance away from that bolt that's causing it to twist. So by the definition we are going to use for 2D, a force times its perpendicular distance away from a point is going to be the moment that it imparts on that point. So for example, for F, if we knew this distance to go perpendicular from F to A, then we could just multiply that by F, and that would be the moment that F causes around point A. This distance, though, is not easy to find normally. So instead, what we're going to usually do is instead of trying to find that distance, we're going to break F back up into its components along our coordinate axes. So in this case, I'm going to be having the x component of F, and I'm going to have the y component of F. And each of them will have a different distance from A, or a different perpendicular distance from A. So really what we're doing when we're measuring distances is we want to know how far is it to a perpendicular line that goes through our point of interest. So for example, from the horizontal component of F to A, we are looking at this distance here. So this is perpendicular to the x-axis. We're going to a line that passes through A that's also perpendicular to, or parallel to the x-axis, that distance is going to be the distance we use for the moment caused by the horizontal component of F. And then the vertical component of F, we do a same thing. So we want to go to the line that's parallel to that force that crosses through A. So let's start with the F here since we're already here. Let's start with just the force. What is the component of F that is horizontal, or the component of F that is along the x-axis? 4/5. Right, so if F is the magnitude of the force, 4/5 of it is parallel to the x-axis. Right, so that is the force, and we multiply that by the distance that that component is from A. Again, this is parallel to the x-axis. We go to a line that crosses through A, also parallel to the x-axis, and then that will be the distance we use for this force. So what is that distance for the horizontal component to A? It's just the 12, because we look at where this force is acting. So that's going to be 12 feet away from A. Also, what we need when we're in 2D is we have to determine, will that be causing a counterclockwise or a clockwise moment around our point? So the way to do this, especially it's good on paper, is you can imagine if we're holding our pencil at the point of interest A, and we were to push in that direction of Fx, which is to the right, which way would the paper want to spin if we were just holding down on A? Right, so the paper would want to spin clockwise, so this is causing a clockwise moment around point A by right, it's a negative moment in that case. Remember, a positive moment will be counterclockwise, negative will be clockwise. So we have to manually put in that this is going to be a negative moment around that point A. Right, so the force, or in this case the component of the force, times the distance that force acts perpendicularly from our point A in this case. All right, so that's just the moment caused by the horizontal component of F. What is the moment caused by the vertical component of F?
0.
Right, that will be 0, because again, if we draw how much is parallel in the y direction, that will have its line of action passing through A. So the rule is if the line of action passes through our point of interest A, or the point we want to know the moment about A, it will have no contribution to the moment because its perpendicular distance is 0. So the force is on the same line that's parallel to A. So the force F causes, its contribution is due only to its horizontal component, but there's also a moment caused by that force P that's acting up here. So we want to know what is the contribution also around point A from force P. So we want to do the same thing. We want to break force P into its components because finding that perpendicular line is not going to be easy. All right, so if we draw this in its components, we are going to first look at the horizontal component of P and then the vertical component of P. So for the horizontal component of P, how much of P is going to act along the x direction?
30 sine of cosine of.
Right. In this case, it would actually be 30 cosine or sine of 45. Because it's 45 here or 45 here. So because I indicated this 45, I'll say it's cosine 45. So that is the amount of force P in the horizontal direction. Notice here, for the moment calculation, I don't care what that this is in the negative x direction. I'm not counting that in 2D. I just care about its magnitude for the moment. Right? And then its distance that acts from point A. Right? So this one, it acts along this line. This line is 18 feet from the parallel line that goes through A. So this has a distance of 18. Then I go and I determine, is it going to be counterclockwise or clockwise around A? So again, holding down on A, if I drag my finger in that direction, it's going to go counterclockwise. So the moment contribution from this component of force is positive. Right? And then finally, there's the vertical component of force P, which is going to be acting down. But again, its line of action is also on this line that cuts through A. So the vertical component of force P will also have no moment contribution because that perpendicular distance is going to be 0. So the only things that do contribute are the horizontal part of F and the horizontal part of P. The other two dropped out because they were 0. In this case, because we know it's in equilibrium, that left-hand side, that net moment is 0, so we're going to be able to solve this for what the value of F must be. Right, so if we move this over, we're going to get that F is a positive value. And if we solve this one equation for that one unknown, we're going to get that F is approximately 39.8 pounds.